Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Fanola Oluwa and I'll be walking you through the physics course. Today we want to quickly consider the simple alternating current circuits, and under this topic we'll be looking at the nature of alternating currents and voltage. We'll be looking at the graphical representation of alternating current and voltage. We'll consider the peak and root mean squared values of alternating current. Also, alternating current circuits, we'll look into resistors, capacitors, and inductors. And also, we'll look at their connections in series, that is, resistors, inductors, and capacitors, inductors, as well the resistor, capacitor, and inductor connection in series. We'll look at the vector diagram of the resistance, inductance, and capacitance series connection, the resonance and power in this series, in these connections, and also we would focus on power in alternating current circuits. So let's begin. What is the nature of alternating current and voltage? By default, when we say alternating current, it means that the current is not linear. It means it moves up and down. It moves within the upper limit and the lower limit. In the production of electricity is being produced by rotating a coil between an electric field, a magnetic field rather. It's rotating a coil within a magnetic field. This leads to the induction of electricity within the coils. When this induction takes place, the kind of electricity that is being produced is described as alternating current. The current fluctuates between 0 and the maximum. It fluctuates between 0 and the maximum. Also, sometimes it fluctuates between the lower limits and the upper limits. That is, it may not be 0 and the maximum, it may be the maximum negative value and the maximum positive value. To calculate the amount of current generated at every instantaneous position, it's calculated as P equals to IP, which IP represents the peak value of the current, IP multiplied by sine omega t. IP multiplied by sine omega t. Omega, of course, is our speed, angular speed of the current, and the t is the time, the specific time. Let's take a look at the graphical representation of current and voltage. If we want to represent them, we can represent them on in a waveform. We could have our currents going something like this. But our voltage does not start from the same point as our current. We'll have our voltage going something like our voltage goes at this is the current and this is the voltage. It moves at a different distance. One of them leads the other. One of them leads the waveform while the other follows. One of them leads while the other follows, of course, and the distance between them is regarded as phi. which is the distance. This is our T and this is our V I. So one of them leads while the other one follows, depending on the nature of the system. Okay, let's quickly consider what is the difference between them is described as the phase angle. That's the difference between the two of them is described as the phase angle. The peak current is the maximum current produced, that's our IP, and the peak voltage, of course, is maximum voltage, VP. So the peak current is the maximum current, the peak voltage is also the maximum voltage. But also there are other things that should be noted, such as apart from the peak current, there is also what is described as the root mean squared voltage or root mean squared current. The root mean squared voltage or root mean squared current, that's VRMS, is calculated by VP equals VP over root 2. Same thing applies for the current. RMS, that's root mean squared. IP, that's peak of current divided by the square root of 2. So those are the way expressions for calculating the both of them. Before we go further into looking at other things, in a few seconds some questions will be displayed on your screen. I'd like you to answer them. We want to see what you've understood from what is being taught in this lesson so far. Alright, let's consider alternating current circuits in resistors, inductors, and capacitors. We already know from our Ohm's law that V equals to IR. That's what we have been taught, V equals to IR. Well, this law does not change in any of the expressions. The only introduction is the fact that we know that our I is not exactly I as it used to be. Our I is now I sine the omega t, and we'll multiply that with our R. So depending on what I, of course this I is a instantaneous I, so we can use small I to represent that, the instantaneous current at every point in time. So depending on the time, we can use that to calculate our voltage, and we can also use the idea even to calculate our resistance. Of course, if we are considering VP is going to be IPR, or rather IP sine R. So all these expressions are just for us to keep at heart. Many of them might not be used in the course of your work, but some of them will find a lot of use. In a few seconds, some question formulas will be displayed on your screen. These are the basic formulas which would find a lot of use in physics when it comes to alternating current calculations. So the formulas we'll be using when we're working with resistors, we'll be using the formulas VR, that is voltage in resistor equals to IP, that's maximum current multiplied by R. And also for our inductors, we'll be using VL, which is equal to IP multiplied by XL. XL talks about the reactance due to the reactance offered by the inductor. Reactance offered by the inductor, it can be calculated as omega L, or which is also calculated as 2 pi FL. That's when we have the frequency, you can go ahead to do that particular calculation. Same thing applies to capacitors. The voltage produced in the capacitor is current multiplied by the reactance of the capacitor, and the reactance of the capacitor is calculated by the reciprocal of 2 pi FC. That's where C is the capacitance. Also, the table is going to be displayed on your screen just about now to shed more information about our circuits. In this table, we have our electrical circuit components. Circuit elements, we have resistors, we have the formula, of course. The phase angle of the voltage in resistors, the phase angle of the voltage is in line with current. It is in the same phase. Voltage and current are in the same phase. But in inductors, the current leads the voltage by 90 degrees, and in capacitors, the current lags behind the voltage by 90 degrees. So let's take into consideration the LC, the different kinds of circuits, that's reactance. Let's consider reactance and the different kinds of circuits that they offer. So when we talk about reactance, we're talking about total resistance or impedance. Yes, impedance, that's addition of all the resistance offered by the different components. Addition of all the resistance offered by the different components. In a particular, let's start with the LR circuit. The LR circuit. Our L there indicates the inductors, and the R represents resistance. So in the LR circuit, we'll have something like the connection of an inductor to a resistor. The connection of an inductor to a resistor. Of course, we know that in the inductor voltage in current leads voltage by 90 degrees, and in resistor, currents and voltage are in the same phase. Thus, when we want to calculate, we calculate the inductance of the inductor, that's the component of resistance of the inductor, which we gave the formula earlier as 2 pi FL. When we calculate this, also we calculate our resistance, and then we can add them together. The total impedance, that's Z. The impedance created will be equal to the square root of R squared plus the inductance squared. Why do we use the square root of R squared plus inductance squared? When we plot the graph of their voltages, we'll find our resistance moving in this direction, and we'll find our impedance and the reactance of the inductor moving in this direction. So this would give the summation of both of them. So this squared plus this squared should give us our Z. That's how we came up with the formula. So you can identify this impedance as ZRL. RL to show that it contains resistance and impedance. How about considering the RC circuits? In the RC circuits, we are having a resistor and a capacitor. In the RC circuits, we have resistor, R, and capacitor. Let's take away the ones because they have no use. So, in this kind of circuits, what do we note? Of course, we have to calculate the reactance of the capacitor, and that's calculated as 1 over 2 pi FC. Now, peradventure, you are given the angular velocity or angular frequency of the system. You can use it directly. The same thing applies to this, because our angular speed is 2 pi f. We can use it directly as well. So we have that, and we also have our resistance. Now, in this particular case, the diagram looks like this. Our resistor is always on the horizontal, but our capacitance is downward. It is 90 degrees. The voltage is leading the current. The voltage lags behind the current by 90 degrees. The other one, the voltage leads the current by 90 degrees, so it stands up. But this time around, the voltage lags behind the current by 90 degrees, so it turns the other way around. So this is the characteristics of, and there is a 90 degrees between them. So this is our ZRC. Thus, our ZRC can be given as ZRC equals the square root of R squared plus XC squared. So you can note that. Yes, I almost completely forgot. There is a phase angle. The phase angle of each of them. Let's start from the up one. The phase angle of RL circuits is calculated by arctan of R over L. The phase angle, I forgot to mention this earlier, of our inductor resistor connection would be given by the arctan of XL over R. And same thing applies here. The phase angle of RC is also equal to arctan XC over R, as one of them is leading the other. How about in an LC circuit? An LC circuit, that's the inductance capacitance circuit. In this, we have something like we have the inductor, we have the capacitor, and there it goes. Now, it should be noted that our inductance will be calculated as 2 pi FL, which is also the same thing as omega L. Our capacitance will be calculated as 1 over 2 pi FC, which is the same thing as 1 over omega C. The diagram for them, we have the inductance up and capacitance down. So this is our XL, this is our XC. Judging by this, we can always say the sum, their impedance LC, will be equal to XL minus XC, because of course it's on a straight line, so we can take them out directly. XL minus XC. So that is the impedance. And well, there is no phase angle between them. The phase angle between them is equals to 180 degrees, which is 0. Arctan 180 degrees is also equal to 0. So, with all this information provided to us, what would, of course, the phase angle between them, we will not be asked to calculate it because it is already known. Judging from our diagram, the phase angle between them is 180 degrees because they are on a straight line. So, with all this information provided to us, let's take a look at what our RLC circuits would look like before we go into calculating, looking at the vector diagrams, and then we start doing other calculations. Our RLC circuits, of course, that will be something like we have resistor, inductor, and capacitor. Resistance, inductance, and capacitance. So our resistance will be calculated as R, our inductance, that's XL. We also know how to calculate that by now, and also our capacitance is there. We know that the relationship between capacitance and resistance, when we draw the diagram, or from the diagram of what is happening, we have something like this. This is our inductance, this is our capacitance, and this is our resistance. So for us to get something like this, we have to find the difference between these two. So if we find the difference between these two, we'll have something like, our diagram will now be XL minus XC. Of course, we can use that in the equation. So that gives our impedance RLC to be equal to the square root of R squared plus, in bracket, XL minus XC all squared. So this is how we calculate the impedance for the whole setup. And when we want to calculate the phase angle, the same manner, we use arctan of XL minus XC divided by R. You can use that to calculate the phase angle. Alright, we've spoken about this. Of course, when we talk about the vector diagram of the RLC circuit, that is the resistance, inductance, and capacitance series connection circuit, we are talking about this diagram that we have been drawing all along. Now, there are certain things to note. When our XL is greater than XC, it suggests that the current leads. Voltage. So it means the current will come before the voltage, and the phase angle can be calculated by the expression. When our XC is greater than XL, it suggests that the voltage leads. The voltage leads the current, and the expression is still provided. The angle between them is also given by the arctan of what we have on the board. So we can always easily just do the maths. And let's take an example on this topic. Let's quickly take this question. The question says you should consider the description above. Of course, yes, we have a resistance given to us 300 ohms. We have our inductance given to us 60 millihenries. We have capacitance, that's 100 microfarad. We have voltage 50 volts, and angular speed, that is angular frequency, that's 100 what's it called? 100 pi radians per second. So we're asked to calculate the impedance. Impedance is simply the addition of all the reactance. So we know our resistance to be that, so we can calculate the reactance of the inductive reactance as omega L, and of course that's 100 times 60, 100 pi times 60, which gives us 60, that's 6,000 pi millihenries, which is the same thing as 6,000 pi millihenries, same thing as 6 pi henries. Let's keep that way for now. We would work on the pi soon. Also, we'll come to the capacitance. That's a function of the capacitance. That's, after us calculate this, as 1 over this, and of course that's 1 over 100 pi multiplied by 100 micro is 10 raised to the power minus 6. So we'll multiply it out. 100 times 100 gives us 10,000, that's minus 4. That leaves us with 1 over pi multiplied by 10 raised to the power minus 2, which gives us, when minus 2 goes up, we'll have 100 over pi, and it is in, of course, our answer here is not in henries anymore. It's not in henries anymore. Just here, I'm considering, okay, times 10 raised to the power minus 3, because of the milli. I'll have this as our reactance, ohms. Of course, this one also comes out in 100 over pi ohms. Now we can introduce the value of the pi and get actual values for this, and can introduce the value of the pi and get actual values for inductance. Our actual value for inductance, our values for, we have our values for inductance, reactance of the inductor and reactance of the capacitor. So we can go ahead and use our formula for impedance. Impedance equals, that's impedance RLC equals the square root of R squared plus, in bracket, XL minus XC all squared. So here we'll have R squared is 300 squared, and then we'll have minus, into bracket, our XL is 18.86, this plus there, and our XC is 31.82, and all this will be squared. So our Z would be equal to, well, we'll use our calculator, 300.3 ohms. So to calculate our total impedance is, this is 300.3 ohms. Alright, we are asked to also calculate the current and resonance frequency. The current and resonance frequency. Current and frequency at resonance. At resonance, it means the impedance and the capacitance, they cancel each other out. That is, impedance and capacitance, they cancel each other out. This is on the horizontal. So at that particular point in time, our impedance at resonance equals R. Well, we've not really talked about resonance. We'll talk about resonance in a few, but let's do the calculation and we'll come back to that. So our I will be equals to V over R. because we're considering impedance at resonance. So that will be 50 divided by 300. And of course, we'll divide 50 by 300. We would get 0.17 amperes. So that's, and also to calculate frequency at resonance. Frequency at resonance equals to 1 over square root of LC. Frequency at resonance equals to 1 over 2 square root of LC, 2 pi square root of LC, 1 over 2 pi square root of LC. So we'll calculate that. That will give us 1 over into brackets 2 pi. Let's come into this place as our L is 60 times 10 raised to the power 3 minus 3. C is 100 times 10 raised to the power minus 6. Because that would give something like about, if you press your calculator, 64.98 hertz. 64.98 hertz. So that's what we'll get as our frequency. Our frequency equals to 64.98 hertz. Alright, we calculated our current as 0.17 amperes and the frequency as 64.98 hertz. So we have to calculate the phase angle between current and voltage. So phase angle, the formula is there, equals arctan of XL minus XC divided by R. XL minus XC divided by R. And when we calculated our XL was calculated as 1.8. So when you use your calculator to calculate this, you get the expression to be minus 2.48. Let's take it all over again. Look, we have our inductance, calculated reactance of our inductor, reactance of our capacitor. Then we have the phase angle formula is written up here. So inserting our values into the formula, we calculate, and using our calculator we get this. Now this negative sign shows us that the system is not having the current leading, rather it's not having the voltage leading, it's having the current leading. That is, the current is leading because we have more of capacitance than resistance, than inductance. Let me leave you with this. Study the expression. When we come back, we'll talk more about resonance and powers in electric circuits. Let's talk about resonance and powers in circuits, in resistance, inductance, and capacitance circuits. Basically, to calculate the resonance, what is resonance? The resonance point is the point at which the current and the voltage start moving on the same plane once again. It simply means that what frequency, at what frequency, resonance talks more about frequency. So at what frequency will the effect of the inductance and that of the capacitance not be felt? To calculate this frequency, it can be calculated using the expression 2 pi square root of LC. 2 pi the square root of LC. The expression was gotten by relating the two different capacitance together, the two different reactance together. we know that the reactance at resonance XL equals to XC. So that's the way they can cancel out each other's effect. The effect that's moving vertically or vertically, that's up or downward, will be equal to 0. So they must be equal to each other for them to cancel out each other's effect. And for them to be equal to each other, it means the frequency, of course, we know that this is 2 pi FL, and we know that this is 1 over 2 pi FC. So when you cross multiply, you have 4 pi squared F squared LC equals 1. I want to find F, so F squared equals 1 over 4 pi squared LC. And when you find the square root, F equals the square root of 1 over 4 pi squared LC. Of course, 4 square root of 4 is 2. Square root of 1 is 1. Square root of 4 is 2. Square root of pi squared is pi. And we can have LC remaining under the square root. So that's how we came about the expression. We get the frequency at resonance. Frequency at resonance means there is no, the capacitance and inductance have no effect on the system. In other words, at resonance, the current and the voltage are in line with each other. They are not at any angle from each other. So what else do we need to bear in mind? How do we calculate the power in an electric circuit? How do we calculate the power in the electric circuit? At resonance, of course, we normally calculate power consider this. We normally calculate at resonance, power will be IV, since all these other ones have no effect, but then it would actually be calculated as P equals to I squared R, or whichever of the formulas you want to use. You can use I squared R, you can use also V squared divided by R. That's naturally at resonance. But of course, since we are talking about the LCR circuits, we're talking about, it means that we are not expecting to always have resonance. So how do we calculate the power? Power is simply calculated as IV cos phi, and of course talk about P. We'll talk about the P's. And what do we mean by talking about the P's? I mean, we have the maximum current multiplied by maximum voltage. That's current at the peak, current at voltage at the peak, multiplied by the cos of the angular phase angle between them. Of course, this is our average power. So these are the formulas that we'll be working with in the course of these particular questions of all this. So I haven't spoken about the simple alternating current circuits, that's the AC circuit. We looked at the nature of alternating currents and voltage. We spoke about the graphical representation. We looked at peak and root mean squared values of alternating currents and also voltage. We also spoke about the alternating currents reactions in movement in resistors, inductors, and capacitors. We then focused on calculations of LR circuits, RC circuits, RLC circuits. Then we looked at the RLC circuits as well. We also looked at resonance and power in the system, in the AC system. So I haven't spoken about all these things. In a few seconds, some questions will be displayed on your screen. You are expected to attempt them. And having attempted them, if there are any one of them that is still proving to be difficult, if there's any of them that is still proving to be difficult, you can go over the video one more time for better clarity.